Hello everyone, my name is Florentin Putz and welcome to this tutorial on the Hilbert Transform. So I noticed that some of you still have trouble to understand the Hilbert Transform and how it relates to AM, QAM and SSB. So I will explain it to you again, and I hope at the end of this tutorial it will become clear to you. So let's start with a quick refresher of what modulation is all about. So when modulating a signal, we have a baseband signal at the low frequencies, we have a carrier frequency and a carrier wave, and we have a passband signal at the high frequencies. So in this example here, we have a digital baseband signal, which is close to 0 Hertz. This is what characterizes a baseband signal, is that the whole frequency contents of the signal are at the low frequencies near 0 Hertz. And if we actually want to transmit the signal, we modulate this baseband signal onto a carrier wave and we receive a passband signal. And this signal will have all frequencies close to the carrier frequency of Fc. So in this example, we use amplitude shift keying, where the baseband signal modulates the amplitude of our carrier wave. So sometimes the carrier wave will be on and sometimes it will be off because the baseband signal was at 0. Okay, and you might wonder, why do we need this modulation process? Why can't we just transmit everything at baseband? And the reason is, think about what would happen if everyone would transmit at the baseband. Different people would transmit at the same time, at the same frequencies, and so these signals will interfere and the receiver will not get a clear signal from one specific sender. So because we want to use a shared medium at the same time, we allocate different frequency bands to different applications and allow them this way to transmit at the same time. And using modulation, we can transmit the same baseband signal to different carrier frequencies and then receive different passbands. Okay, so we already talked about amplitude modulation in our lecture, and this is just a quick refresher of what amplitude modulation is all about. In this case, we simply have a baseband signal, a real baseband signal, which gets multiplied, in this case by a cosine signal, at a certain carrier frequency. And if we look at the frequency representation of this real baseband signal, we will notice that it's mirrored at the y-axis because real signals will have negative frequencies for each positive frequency. So let's look at our carrier wave here. This carrier signal is also a real signal because we can see the positive carrier frequency and also the negative carrier frequency here in this frequency representation. And if we multiply both signals together, we get a real passband signal where the baseband is shifted up to the carrier frequency. And because the baseband also had negative frequencies that are exactly mirrored from the positive frequencies, they really become visible now at the passband because everything here just gets shifted up to the carrier frequency. So here we can see what previously was positive and negative frequencies. And this is still a real signal because we have everything that's in the positive frequencies, we also have at the negative frequencies exactly mirrored. Now we call the lower part of this passband signal, what previously was the negative frequencies, now is the lower sideband, and what was the positive frequencies now is the upper sideband. But because both are exactly mirrored, we don't get any new information from the lower sideband and the upper sideband. It's exactly mirrored. And this is a bit inefficient because we basically transmit the signal 2 times, one at the upper sideband and one at the lower sideband. Now let's look at Quadrature amplitude modulation, QAM, and let's see what is different here. So you can see the upper part of this is the same as with amplitude modulation, but the lower part is not. This is new, and what happens here is that we use a second carrier wave which is 90-degree phase shifted from the previous one. So because we used the cosine signal before, we now additionally use a negative sine wave, which is 90-degree phase shifted from the cosine wave. And if you remember from the lecture, these two waves are orthogonal, so we can modulate them at the same time, add them, and the receiver will be able to again separate this cosine from this negative sine wave and receive the information we encode onto these waves independently from each other. And in this case, because we basically have two baseband signals, one for the cosine and one for the negative sine, we can think of this as a single complex baseband signal, which has a real component and an imaginary component. And the real component, let's call it I of t, is what modulates the in-phase component of our resulting signal. And the imaginary component, let's call it q of t, will be the quadrature component of this. And the reason is that the cosine is basically our in-phase component, because the I of t will modulate the in-phase, the cosine, and the q of t will modulate the quadrature component on the negative sine wave. And here you can see the mathematical description of this block diagram above. And these equations should be familiar to you. It's basically exactly what you see here, just written down. And in the end, you sum both parts of this and get a real signal and transmit it using your antenna. So let's look at the frequency representations of all these signals. We, in this case, now have a complex baseband signal because we have two different signals, the real part and the imaginary part. And because it's complex, it's not mirrored anymore. So in this case, the negative frequencies can be freely chosen and are independent of the positive frequencies. We also have a carrier signal again. And as a result, we get a real passband signal, and you can see that it's real because it's mirrored again. So the positive frequencies are exactly mirrored in the negative frequencies. And the reason it's real is because the real and the imaginary part of this complex baseband signal are each individually real. And if we modulate them using a real cosine or a real negative sine, this will still just be real. And if we add it, it's still real in the end. And you can see again, we have a lower sideband and an upper sideband, but in this time, they can be different because our complex baseband signal had different negative frequencies than positive frequencies. So we can influence the upper sideband and the lower sideband separately, and so we don't waste information anymore, because now, compared to amplitude modulation, it doesn't have to be the same in the upper sideband and the lower sideband. Okay, now let's quickly come back to amplitude modulation. And you can think of amplitude modulation as a special case of quadrature amplitude modulation, where we just set the imaginary part of our complex baseband signal to 0. So we will have a real baseband signal again. And you can see it here as was before. We just get rid of everything that was imaginary before. So the q of t will be removed. And here it's removed again. And so we will just get what we had previously with amplitude modulation. So just a real baseband and a real passband. Now let's come to single-sideband modulation, which is basically like a combination of AM and QAM, which we saw before. So this time we choose a special q of t, which is dependent on I of t, on the in-phase component. And because we have a q of t, it will be a complex baseband. But the idea is to choose this quadrature component in a way that the negative frequencies in our complex baseband signal will get cancelled out, so that they will be removed. And if we can do this, we get rid of the lower sideband in our passband signal, because we will just have positive frequencies in our baseband signal. But still, this is a complex baseband signal because it's not mirrored, right? We remove the negative frequency components. So in the end, we have just the positive frequencies in our complex baseband signal. And you might wonder, okay, how can I construct such a quadrature component, such an imaginary part of our complex baseband signal, that we actually remove the negative frequencies? And the answer to this is that we use the Hilbert transform. So this H here is the Hilbert transform, and the Hilbert transform of the in-phase component will be our quadrature component. And if we then sum it as a complex baseband, what we actually get is called an analytic signal. And analytic signal X plus just means that it doesn't have any negative frequencies, so it just has positive frequencies. And this is a complex signal, which is exactly the same as our real baseband signal before, but it just doesn't have the negative frequency components. And to construct this analytic signal, you apply the Hilbert transform and add it as an imaginary part of your baseband signal. Okay, so let's look at an example to show you how to actually calculate the Hilbert transform and also how to use it to build an analytic signal. And for this example, I will show it to you using a cosine wave. And the reason is that, as you know from the lecture, every signal can be thought of as a sum of sine and cosine waves. And I will show it to you for a cosine wave. Maybe at home you can do it for a sine wave, this derivation. And then this should hopefully convince you that the Hilbert transform and the construction of analytic signals also works for any arbitrary signal that is based on these cosine and sine waves. So in this case, I use the cosine wave with a frequency of 10 Hz. And just as a shorthand, I will use this abbreviation omega 10 here, which stands for a cosine wave with a frequency of 10 Hz. So just this 2 times pi times 10 Hz, I will write it as omega 10. And omega is the symbol that we usually use for the angular frequency or the circular frequency. So I just replaced this part by omega 10 here, which is a bit easier to write because we will have to write this part a couple of times on this slide later on. Okay, so now let's consider this frequency representation of this cosine wave here. Now remember that in the frequency domain, every frequency has a magnitude and a phase, and we can also look at this as a complex frequency representation, where we have the phase built in using the relationship between the real part and the imaginary part. And as this cosine wave is a real signal, we have the mirrored negative frequency of minus 10 Hz here that corresponds to the positive frequency of 10 Hz. And the cosine wave, if you look at the representation using Euler's formula, you might remember this formula from your math classes, you can deconstruct this cosine wave as a sum of two complex exponentials, which both have magnitude 1/2. You can see it here, this both has a magnitude of 1/2, and here for the negative frequencies and here for the positive frequencies. And this shows you again that this cosine wave actually consists of two elements with a negative frequency and with a positive frequency. And as the coefficient in front of the exponential is a real number of 1/2, this phasor here will point in the direction of the real axis. So the imaginary part of these frequency phasors here will be 0. Okay, so what I will show you in the end is how to construct the analytic signal that corresponds to this x of t here, this cosine wave. And to do this, as I showed you on the last slide, is we need to calculate the Hilbert transform of our signal. And I haven't actually told you yet how to calculate Hilbert transforms, but it's actually quite simple. So all you have to do is you have to multiply your positive frequency components by negative j, so the negative imaginary unit, and you have to multiply all negative frequency components by plus j. And you might remember from your math classes that in the complex domain, and this is actually the reason why we use it, we can represent rotations by multiplications with the complex number j. And any multiplication by a complex number can be thought of as a rotation in the complex plane and also some scaling. So this is how the Hilbert transform of our cosine wave looks like. And so let's look at this green positive frequency component here first. We multiply it by negative j, and negative j basically means that we rotate by negative 90 degrees. So this phasor here that looks at that points in the real axis will now be rotated downwards to point in the negative imaginary axis. And you can see this here, because multiplication by j is multiplication by plus 90 degrees. So this real part by j would be imaginary, and then by j again would be negative real, and then by j again would be negative imaginary, and then back to the real positive part again. But in this case, we multiply by negative j, so this phasor now points downwards because we rotated it. Now let's look at the negative frequency component. According to the Hilbert transform, we have to multiply it by positive j, so this is just multiplication by 90 degrees. So this real part now will point upwards to the imaginary axis, because now it will be imaginary. And you can also verify this by looking at the math notation of this here. And you can see here that we now have a minus j in here multiplied, and we now have a plus j in here multiplied. And this is actually very interesting. What we get is the sine wave. So the Hilbert transform of a cosine wave actually is a sine wave. So yeah, and this is what the frequency, the complex frequency domain of a sine wave looks like. Okay, now the next part is, remember that the analytic signal means that we take our signal as the real part, and we take the Hilbert transform as the imaginary part. So to build the imaginary part, we have to multiply by j again. And so we now already know how multiplication by j works. So in this case, we multiply the positive part by j, which is a rotation of 90 degrees again. So we rotate it back to the real axis. So it will now point again back to the real axis. And the negative part, we multiply by j as well. And it will now point to the negative real axis, because we multiplied an imaginary number by j. So j times j is negative 1. So now it will be negative 1 instead of j. Now to form our final analytic signal, we add these two things, and now we have a complex signal, the analytic signal x plus, and we basically can think of this by adding the phasors of this original real part here and this imaginary part here. So we add these phasors one by one. First the positive part, and we have two phasors that point in the same direction at the real axis, and we sum them and get a larger one that also points at 10 Hertz in the real axis. And both components had a magnitude of 1/2, so the sum of those will have a magnitude of 1. Now let's look at what happens to the negative frequency phasor. In this case, they point to opposite directions and have the same magnitude, so if we sum them, they actually cancel out. So we have no negative frequency component, and this is exactly what we wanted and why we use the Hilbert transform. And this should give you also some geometric intuition on how the analytic signal actually gets built up by rotating the phasors using the Hilbert transform and then rotating them again using multiplication by the imaginary unit. And To summarize, the core idea of what we did is we used our real input signal and added an imaginary component to it, which in the summation will remove our negative frequencies. And if you want, you can pause the video and try this also out with the sine wave as an input signal. And this should then show you how the negative frequencies again will cancel out, and you will be left with a complex signal with only positive frequencies. And of course, the signal is complex because it's no longer mirrored. The negative frequencies will no longer be mirrored versions of the positive frequencies. Now, if we go back to single-sideband modulation, you can now see how we were able to construct this complex baseband signal here, which doesn't have any negative frequency components anymore. And if we now perform quadrature amplitude modulation on this, we actually get a passband signal, a real passband signal, with just an upper sideband. So we don't waste the lower sideband anymore, because we just shift this up, and this just doesn't have negative frequencies, so we also won't have a lower sideband. And this is a more efficient form of modulation, because we don't transmit the same stuff twice in the lower and the upper sideband. We just transmit one of those sidebands by using a complex baseband signal. So I hope this tutorial cleared this up for you, and you hopefully now understand how the Hilbert transform works and how it can be used to construct a single sideband modulated signal. And with this, I wish you a nice day.